Hey chemists, how you going? Just want to go through the solutions to the amines and amides quiz that was administered at the end of the holiday break. So I'll just kind of chop and change through the questions and the solutions. I had these printed out ready to go for you guys back with your quiz, but we've ended up going into lockdown. So I have those in my possession, and you've seen grades being released on Sector. So the first question here was to do with methamphetamine. So this is the chemical structure of methamphetamine. And we want to draw the structure in a solution of pH 2. So the significance there is you need to think, what does that mean? So pH 2 is acidic conditions. Acidic conditions have an excess of protons, so H+. So basically we need to think which functional group here is going to accept a proton if there's excess protons in solution. And that's going to be the amine functional group, which is basic. So basic amines can be protonated in acidic solutions. So what happens is, and I'll just quickly Alt-tab here, you get an extra proton being attached. So you get an extra hydrogen, and you have a positive charge. Now, the important thing is the positive charge is clearly on the nitrogen, because that is the atom that has an extra proton being attached. So therefore that positive charge is on the nitrogen. Okay, so making sure you clearly show that. So 2 marks there. If you might lose a mark, and some of you did, because you did the right thing, but the positive charge was over the hydrogen instead of over the nitrogen. So that's actually kind of important how we do that. Just go to the right tab here. Cool. So explain why methamphetamine is usually administered in the form of its salt rather than an amine form. Now, methadone can be used for medicinal purposes, so that's why we're kind of referring to that there. So the reason is the positively charged ion forms stronger ion dipole interactions with polar water molecules, because we're talking about action in the body. So in the body, there's lots of water, so we want to talk about solubility with water. Compared to the limited degree of hydrogen bonding that is possible between the amine molecules and the polar water molecules. Essentially, just the fact that ion dipole is stronger, so you've got a stronger interaction, so it's more soluble. And 4 marks associated with that. So I guess it's kind of hard to get 4 marks from this, I found. 3 marks is probably more suitable, but you need to refer to the aspect of the protonated amine. So the fact that it's positively charged is important. The fact that there's strong ion dipole interactions. So you need to talk about the fact that that's a stronger interaction than hydrogen bonding. You're talking about the fact that it's interacting with polar water molecules. So there was nothing in the question talking about why is it more soluble in water. It just said usually administered in the form of a salt. So administered, that means why is it delivered there? So here, a synthetic amine that is a powerful stimulant of the central nervous system. So we're talking about the effect on the body. Okay, so that's why what's in the body, lots of water in the body. And we talk about this salt version for medicinal purposes. We talked about that looking at carboxylic acids as well, how they can be administered in the form of a salt. So that was kind of like a segue into that. So that's where you kind of get that information from, okay? And you want to talk about hydrogen bonding as the alternative. Like, that's not as good. So that's why it's administered in the form of its salt. All right, so similar type question here, talking about synthetic drugs are complex amines, and here's an example. So circle the functional group that can act as a base. So it's the amine functional group. So this is what you're circling. A few of us didn't get that. So, I mean, what other functional groups are there? There's an aromatic or a benzene. So that there is a hydrocarbon that's non-polar, it's not basic. This is a carboxylic acid, so that's acidic. This is an ester, that's neither acidic nor basic, okay? This is the only base that exists. Why is it a base? Because it can accept a proton. So that was the next question. Why can it act as a base? A lot of us said amines have the ability to accept a proton because that's what bases are. They're proton acceptors, so that's good. Why is it able to do that though? Part of the reasoning is the lone pair of electrons. So nitrogen has one non-bonding pair of electrons, and therefore it has space to be able to accept that proton, okay? If an atom doesn't have a lone pair of electrons, it's going to be too crowded and it can't accept another proton. Describe how the above synthetic drug could be made more water soluble. Now this is an interesting one because a lot of you guys kind of gave the right answer, but I didn't give you the mark. And I'll explain why in a second. So why is it, how could you make it more water soluble? A lot of people said give it a proton or let it accept the proton, okay? But describe how it could be made more water soluble. That's implying how could you make it more water soluble? So what could you do as a chemist? So as a chemist, you could react this with an acid, okay? Now, if you say react it with an acid, that's an okay answer. It would probably be better to actually describe a reagent that you could use as a chemist. So I've said add dilute hydrochloric acid to it. Now you could have just said add hydrochloric acid, you could have said add nitric acid, you could have said add sulfuric acid. Any reagent, a specific reagent that will allow a proton to be added to this to make a salt would be the correct answer. Okay, now we're into amides. So this amide is a tick repellent. Looks like that. Name the carboxylic acid used to prepare it in the laboratory. So where is the amide? Okay, so an amide is C double bond O, so your carbonyl, and then a nitrogen, and then usually you have a hydrogen attached to it. Now this one here has a different kind of chain attached to it, but basically this part here is the amide. All right. So the carboxylic acid part of the amide, you want to get a line chopping this CN bond, okay? Because the carboxylic acid is this part here. And what's come off? An OH, okay? Hydroxide has come off in order to make water because a condensation reaction produces an amide functional group, okay? So basically what you'd want to do is you'd want to redraw this and just add OH at the end. Now the name of that is basically you've got 1, 2 carbons and then you've got the carboxylic acid functional group. So that would be methanoic ethanoic acid. Okay. A lot of us were not able to name ethanoic acid, which means our naming conventions for carboxylic acids just need to be worked on a little bit. Okay. Methanoic acid, propanoic acid, butanoic acid. If you see that COOH, that's how you name that. So the type of chemical reaction to prepare this amide and name the small molecule eliminated. The type of chemical reaction is condensation reaction, and the name of the small molecule eliminated is water. Basically, water drops off when you react an amine and a carboxylic acid to form an amide. A lot of us didn't get that, and that might just be that we hadn't looked at amides properly. Draw the two products formed when the above amide is hydrolyzed under basic conditions. So this is kind of like what I said. Chop this up, put OH here, and put a H next to this N. So draw this, copy this, chop that, add a H, and you get that. So the convention is exactly the same, just have a H there. This one here, chop that, add OH, and then that's going to be your molecule there. So actually, my mistake, it says hydrolyzed under basic conditions. So you're not going to get a carboxylic acid under basic conditions. So everything that I said is correct, apart from the acidic hydrogen. That's not going to be there because in basic conditions, this acidic hydrogen will be donated to the hydroxide ions that are present in basic conditions. So basically what you're going to get is a carboxylate ion. That should have a negative charge on there. It just doesn't show very well when I photocopied this. So that's a carboxylate ion. Finished off there. Okay, so this is the exam question. So we've got two amines. So we've got TMA and putrescine, and they're amines that are produced by bacterial decomposition of compounds in animal flesh. So TMA, you've got a nitrogen and you've got 3 methyl groups. So this line here is this is a skeletal form. So this is CH3, CH3, CH3. Okay, and then this, we don't need to talk about that at the moment. So it's TMA primary, secondary, or tertiary. It's a tertiary amine because it has 3 hydrocarbons attached to the nitrogen. So tertiary is the most crowded amine that you can get. A secondary amine would have 2 hydrocarbon chains and 1 just with a hydrogen. Okay. Primary would have 1 hydrocarbon side chain and 2 hydrogens. All right. So tertiary is the most crowded. Primary is the least crowded. The systematic name of putrescine. So we've got 2 amine functional groups on either side. So it's a diamine. The hydrocarbon chain is 1, 2, 3, 4 carbons long. So that's butane. And the amine functional group is coming off of carbon number 1 and carbon number 4. So that's why it's butane 1,4-diamine. So we're explaining why TMA has a low boiling point. So 3 degrees Celsius. Evaporates easily, causing a fishy smell. So the first thing here is you want to, so it says with reference to the structural formula. So point 1, I'm referring to the structural formula. So I'm saying it's a small molecule. It has slight polarity due to the nitrogen-carbon bonds and trigonal pyramidal geometry. Okay, so trigonal pyramidal because it has 3 bonding pairs of electrons and a lone pair of electrons that is not shown here, but nitrogen is in group 5, can form 3 chemical bonds, and we've got 2 non-bonding pairs of electrons. All right, so that would make a trigonal pyramid. But it's a predominantly non-polar molecule because methyl groups are non-polar. Okay. It has weak dipole-dipole interactions experienced between molecules. So even though I'm saying it's predominantly non-polar, there's still polarity in these bonds. So therefore, there is a dipole because of the fact that it's trigonal pyramidal. So we've got dipole-dipole interactions. So that's what I'm describing between the TMA molecules. A relatively small amount of energy is required to overcome these interactions, hence a low boiling point. All right. So I'm saying weak and small amount of energy because the question says it has a low boiling point. So when I'm describing it, I'm saying this is why because these are the secondary interactions and they're quite weak. Okay. I know they're weak because it says it has a low boiling point. All right. So when you add lemon juice, it decreases the fishy smell. So this is basically lemon juice is acidic. So acidic conditions. So essentially the amine is going to become protonated. So what I've done is just added a hydrogen. Now I could have drawn another bond coming off and done a hydrogen like that. If I was doing that, I would probably be doing a wedge line or a dashed line. The reason for that is to show the 3D structure of this. Because essentially that one would be going out the back of the page or out the front of the page, okay? Because these lines are coming off like this. Remember, it's a pyramid. So how do you do a pyramid with my hands here? It's a triangle coming off, I don't know. Hopefully you know what I mean by that. The positive charge needs to come off the nitrogen, not off the hydrogen. So this is an interesting question. Why the fishy smell of TMA decreases when the lemon juice is added? So the fishy smell is due to the evaporation or the boiling of the TMA, and it has a low boiling point of 3 degrees. So we need to talk about the fact that the boiling point increases when it becomes protonated. So I've said the acidity protonates the TMA molecule. Now that's not a mark because I've already done that in the previous question. A lot of you guys, when you answered this, you did that part and that's it. So that was prior knowledge, but I'm just giving it as context. So that's not a mark. It forms an ion, which again isn't part of the mark. Ion-dipole interactions are now experienced between protonated TMA molecules. Now you could also say between protonated TMA molecules and water because lemon juice is predominantly water. That's probably a better answer because basically it adheres more strongly to something, whether it's each other or whether it's water. The boiling point is higher for the protonated form, hence it's less volatile. Because this is only a 2-mark question, I'm not really going to go too much in the fact that more thermal energy is required to overcome blah, 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 blah. I'm just saying stronger interaction and specifying the interaction and saying the boiling point is now higher, which means less volatility. Now, volatile means how much, if a compound is volatile, it means it changes state from liquid to gas quite rapidly, I guess. So you get a lot of fumes coming off. Something that's low in volatility means it's quite stable, so it's not going to start to provide fumes. Okay, so this one here is just the interpretation of a graph. So fish can be classified as fresh when the concentration of TMA is below 1 arbitrary unit. From the graph, determine the length of time from which fish can be stored at 5 degrees. So 5 degrees, I'm looking at this curve here, and the arbitrary unit of 1 is here. So basically, I'm just looking at that point, and I'm going down, and I'm trying to read off that scale. Now, for me, 150 would be here, and I'm about here, so that looks like about 130. So it's 130, but if you are within that range, that's deemed as okay. All right. But the way I do that is just 100, 200, chop it in half is 150. You could chop that in half again, 125. How close am I? You just estimate. Using the values from the graph, determine the effect that temperature has on the rate of formation of TMA in fish. So as the temperature increases, the rate of formation increases. So basically, that's higher, and you make more TMA more quickly because the slope is steeper. Okay, low temperature, the slope is less steep. Okay, so that's indicative of rate. Okay, because rate is formation over time. So temperature increases, rate of formation increases. You need to refer to data, guys. You need to refer to data. So I've said at 150 degrees, a maximum, 15 degrees achieves a maximum in approximately 100 hours, 5 degrees in 300 hours. So I'm just going, 15 gets to the top at about that much time, 100, and then 5, 300, like that. So I'm just trying to refer to data where possible. What effect does temperature have on the final concentration? There's no effect, okay? It gets there more quickly, but at 0 degrees, it gets there eventually, okay? So the trick here is it's talking about final concentration, not rate of formation. There's a difference, so no effect. Thanks, guys. Hopefully you could see maybe a few of those solutions there. I know you don't have your work with you, but hopefully you can get a bit of an idea of what we were going for. Thanks.